All right, today we're looking at topic 11, which is graphing logarithmic functions. We're going to take a look at what the graphs of some logs look like. Remember, logs are the inverse of exponents, which means that their graphs essentially have complete opposite xy coordinates. So if an exponential graph has coordinates 0, 1, then the inverse graph would have the points 1, 0. Another way to think of this is that the graph is reflected across the line y equals x. That's the line where all the x and y values are the same. So most exponential graphs will look like this one on the bottom here. Basically, a reflected version of an exponential. Some characteristics of normal non-transformed log functions: they always have a vertical asymptote at x equals 0. They always have a domain of 0 to infinity. And a log function is increasing over the entire domain. Have an x-intercept at 1, 0 in a range of all real numbers, negative infinity to infinity. This is for non-transformed log functions. This is where your h value is 0 and your k value is 0. So a non-transformed log function is just log b of x, just a log of x. However, this function has the same transformations as regular functions. Any value that is directly affecting the x coordinate will shift it left or right. Because that's inside the function, so it directly affects the input of the function, moving the function left or right. Any number on the outside of the function directly affects the output of the function, which moves it up and down. And these are movements from the parent function. So this assumes that you already know what the parent function is, and you can use these to move it around. We're not going to be graphing these according to the transformations. We're going to be graphing these using a simple table. So the first one we want to graph is just this very simple log. This is the common log. Remember, if it doesn't have a base, we assume that the base is 10. So this is a log base 10 of x. So this is non-transformed. So it has a vertical asymptote at 0. The reason it has a vertical asymptote at 0 is because you can't plug in 0 and you can't plug in negative numbers. So it's not going to exist over here in the negative region because you can't do that. So we're going to start at 1. We're going to start just to the right of the asymptote with our table. So I'm going to plug 1 into this function. So the log of 1, common log of 1. Well, remember, this is asking 10 to what power is 1? And that would be 10 to the 0 power. So plugging in 1 gives a 0, which is right here, 1, 0. Now the next point that I want to pick is the number that would give me the next output, which is 1. It should be the next number that I can take a common log of and get a whole number. The next number I would want to take a common log of would be 10, because this is asking 10 to what power is 10, and 10 to the first power is 10, so the common log of 10 is 1. So plugging in 10 gives me 1. So I'm going to go over here to 10, so 10 is like right here, and I get 1. So as we can see, this is a very steep graph. I only need 2 or 3 points to graph this, and since I'm already off the graph, I'm only going to use 2 points to graph this. And it looks something like this. As we can see, the domain is from 0 to infinity, and our range is from negative infinity to positive infinity, all the way down and all the way up. So this would be plenty for my graph. I only need 2 or 3 points, and these 2 points will be fine because I can't really fit anymore. Now you can technically plug in any point between, well, any point you want. You could plug in 2, you could plug in 3, you could plug in 4 or 5. The only problem with plugging in those points is you would have to use a calculator to calculate it. Okay, if you plugged in 2, you'd have to do log 2 in your calculator, which is just a little inconvenient. Let's take a look at this next one here. So we have f of x is equal to common log, so this is log base 10, of x plus 3 minus 1. Now, this is actually a transformation of the one we just saw. This is a transformation left 3 and down 1 of the graph that we just saw, because the graph we just saw was a parent function, and this is a transformed function. Now, I'm not going to graph it even according to the transformed function, but I do want you to compare this to the graph we just did after we're done and see that it's been shifted to the left 3 and down 1. So, if this has been shifted left 3, then now the vertical asymptote will be at x equals negative 3. Because that is, negative 3 is now the value that makes the inside of the logarithm equal to 0. So this graph will not go past negative 3. So I'm going to start just to the right of that. I'm going to start at negative 2. Plugging in negative 2 means I take the common log of 1 and I subtract 1. So that's 0 minus 1, which is negative 1. So my first point is at negative 2, negative 1. That's the first point I'm graphing. Now, I would like the next point to give me an output of 0. So I need to plug in the next number that's going to allow me to take a common log. Essentially, since the base is 10, I now want this to be 10. So in order to accomplish that, I'm going to plug in 7. Because now I take the common log of 7 plus 3, which is 10, and subtract 1. Common log of 10 is 1, and 1 minus 1 is 0. So my next point would be 7, 0 over here. I could technically plug in any point in between these two. I could plug in negative 1, I could plug in 3, I could plug in anything I want, but these are the easiest points I could use. This is more than enough to graph it. And it looks something like this. Now the domain is no longer from 0 to infinity, it's now from negative 3 to infinity. However, the range is still the same, negative infinity to infinity. The next example, we have a log base 2. Log base 2 look a little bit different. Not really, though. It's going to look pretty much the same. First, we identify the vertical asymptote. However, this is a transformation not of common log of x, but this is a transformation of log base 2 of x. It's going to be a shift right 2 from this function. But I don't know what this function looks like, so I'm not going to worry about that. Vertical asymptote is now going to be at 2, because 2 would cause me to take a log of 0. So my vertical asymptote is now here at 2. So first number I want to plug in is to the right of that, which is 3. Because when I plug in 3, 3 minus 2 is 1. Log base 2 of 1 is 0. So my first point is 3, 0. Now, the next point I plug in should give me an output of 1. The next number I plug in should evaluate to 1. Which means that this, when I plug it in, should be 2. Well, to accomplish that, I need to plug in 4. Because 4 minus 2 is 2, and log base 2 of 2 is 1. So my next point is 4, 1. And it looks like I can fit another point on here, so I'm going to just do one more point for good measure. The next point I plug in should give me 2 after I plug it in, which means that here needs to be 4, because log base 2 of 4 is 2. So in order to accomplish that, I'm going to have to plug in 6, because 6 minus 2 is 4. So plugging in 6 gives me log of 2, log base 2 of 6 minus 2, so a 4, and log base 2 of 4 is 2. So 6 would give me 2. So 6, 2 is right here. I can connect these points. And this is my graph. Oops. As we can see, has a domain from 2 to infinity, because the asymptote's at 2 and it goes to infinity, and the range is negative infinity to infinity. Lastly, here we have a natural log function, and unfortunately I will have to use the calculator for this one, because the only logs that I can evaluate to get whole numbers with the natural log are powers of e, and powers of e need the calculator anyways. So first I identify where the vertical asymptote is, and it's going to be at 0 because it can't take a log of 0, so x equals 0. This is right here. I'm going to pick the first point to the right of that, which is 1, and I'm going to plug that in. So the natural log of 1 plus 5, so that's 0 plus 5, which is 5. So 1 comma 5 right here. Now I could do this the way I've been doing it and try to get 6. However, that's going to be a little bit difficult because the only way I get 6 is by taking the natural log of e. So in order to get 6, I would have to plug in e, because the natural log of e is 1, and 1 plus 5 is 6. But, I mean, that doesn't really help me that much, because where is e? I mean, e's like here at 2.7, so I'm just going to plug in 2 and see how that works. So let's plug in 2. So I'll take the natural log of 2 and add 5 to it. So I'm going to have to put this in my calculator. Natural log of 2 plus 5 is like 5.7. So like right here. All right, maybe I'll do one more for good measure. I'll plug in 3. So natural log of 3 plus 5. Natural log of 3 plus 5, so like 6.1. Okay, not a big difference. All right, well, I kind of got the idea of what this looks like anyways. Something like this. As you can tell, it's shifted up a little bit because of the transformation. Plus 5 shifts it up. Domain is 0 to infinity. The range, negative infinity to infinity. And that's how we graph log functions.